Okay, let's recall what we were doing. Our interest is in describing scattering, where we are imagining that we have particles which are well separated and far past in time. There could be more than two particles, right? It's not necessary that you have only two particles which collide, but you can have n number of particles colliding together. So I'm thinking of several particles which then proceed along some trajectories, okay, and they come close to each other. And of course, we are dealing with interacting field theory, so they interact with each other. So when they are very far apart, we have a notion of how many particles we have, but as they come closer, okay, this notion is lost. We cannot describe any fixed number of particles, okay, and they come close and eventually they collide, and at a later time the picture is that you have from this region several particles coming out. So here these particles were going in, and later you have several particles coming out, okay, and if you wait long enough, you'll see particles which are localized in space with some definite momentum or reasonably well defined momentum and reasonably well defined location, okay. So this region, where somewhere here I will define, okay, t equal to 0, x equal to 0, and also the some arbitrary time when they are interacting appreciably, I will call that time as t equal to 0. That is the picture. Now we have seen that we can define a basis. So whatever the Hilbert space you have, okay, the Hilbert space for the system, okay, you can choose a set of basis states which are called in states, okay, which have the property that if you fold them with appropriate functions, you can arrive at this picture of non-interacting particles which are well separated. And we saw how to create these in states. So we saw that if we have an operator A in dagger, and I'm using A in dagger with K1, and also we have to put this vector because of our choice of normalizations. So if I take this operator and act on a state, in state, which carries these labels K2 to Kn, okay, then it gives me a new in state which carries this K1 label also. Okay, that is what in effect we have learned in the previous lectures. Okay, and of course you can start with vacuum and then have first a single particle state or in state carrying only one label, and then you can repeatedly act with A in daggers to create such states. Okay, and we also saw that if you start with a state which has these labels K1 to Kn, okay, and act with A in of K, okay, I think this I showed you only for case of single particle state, but if you repeat the arguments, you can see that this will give you the following results. I equal to 1 to n 2 omega ki, again because of normalization, delta cube k minus k I, okay, and there is a summation, and you have to multiply with these gets k1 to kn n. So all of these labels which are here, okay, all of these labels you have to put, but a in k will remove the label ki. So that is gone. This label will not be in here. So for example, if you had k1, k2, k3, okay, and if you act with a in k, then if k is equal to k2, then this label will be gone, okay. And if none of these labels k1, k2 and kn matches this label k, then this delta function will be 0, okay, and then the right hand side just vanishes. So it's just removing that. If that label is present, it removes that label and gives you a state or a sum of in states with one less label. And if the label k is not present in this list, then it just kills that state, okay. So just a second. Now this is what we have seen. Now you can repeating similar arguments as we did in the last 2 videos. You can define a out k dagger, which is 1 over square root of z, limit t going to infinity of a dagger t1 minus I epsilon p. Okay, so this is, if you were to discard I epsilon, this is basically a dagger at a very large time. Remember, we had this a dagger of t, this operator, and in this operator we have to put t times 1 minus I epsilon, where epsilon is positive, and take capital T to infinity, and that's the definition of a dagger out. And a out also will define, which is 1 over square root of z times this object, okay, where again you have to take a t, and then in that substitute for the small t, capital T times 1 minus I epsilon, and take t going to infinity limit, okay. So these are these two operators which are which carry this subscript out, and you can check that the states that the basis states which these create are the ones which, if you were to fold them with appropriate functions, they will give you states or particles. They will give you a state which will represent well separated particles in the far future, okay. So where because I am talking about t going to infinity, so you have to repeat the similar arguments as we did for a in, okay, and convince yourself that indeed what I am claiming is true. And once you have done that, you will arrive at the following conclusion, that if you take I will write this in the bra form, not in the ket form, because that is what we are going to use when we write down the S matrix. So you should be able to arrive at this conclusion, that if you take a out dagger k, okay, and act on this bra, then this will remove this label k, okay. So if there is a label k sitting in here, then that will be removed. So similar to the case for in states, you will get 2 omega k I square root times delta cube k minus k I, and then you have this state which has label ki absent, And as before, if none of the labels k1 to kn matches the label k here, then the delta function vanishes, and this, which means that this A dagger out is going to kill this kill this state. Okay. And similarly, you will have, if you take state k2, k3, so and so forth, kn, okay, and out state, and you act with A out of k, and actually not this, but 2 omega k1 square root of 2 omega k1 A out of k1. Okay, that's coming again from normalization. So essentially if you take this A out and act on this ket, this out state, it will insert this label k1. So the state you get carries one more label k1. Okay, so this is equal to this out state. Okay, so this is what you get, and now we are going to utilize this to talk about scattering. Okay, but before I talk about scattering in a process or even in a general, I should first look at the S matrix elements which I had discussed in the beginning of this course. Okay, so let's go to the next sheet. So what do I want? See, the thing is that at t equal to 0, okay, if you are thinking in terms of Schrödinger picture, then at t equal to 0, we are looking at some states, or if you are looking at Heisenberg picture, you can take the states at t equal to 0 and in Schrödinger picture as the states in the Heisenberg picture. Okay, and remember, states do not evolve with time in Heisenberg picture. Anyhow, so you take at the Hilbert space, okay, which is found by these in states, which are basically defined at t equal to 0, okay, which have this interpretation which I have been saying, and if you wait for some time, okay, maybe let me rephrase it. It's not the best way to phrase it. How should I say? Yeah. So these in states are good basis states if you want to describe incoming particles. Okay. But these are not good basis states for describing particles, particles in the far future. Okay, because you know that if you start with some incoming particles, let's say 4 of them, and they come and interact, okay, here, after they have interacted and large time has passed, it might give you in the final state 20 particles, okay, going in certain directions. Okay, and remember how we constructed in states. We took this these limits where the small t went to minus t times 1 minus epsilon, and we took capital T to infinity, and that is what was picking in states. Okay, but then the same in states is not, so let's say you start with an in state in which you have, so you start with a state in far past which has 4 particles. Okay, so that state you will write in terms of these in states which carry 4 labels, k1, k2, k3 and k4, and you'll have sum over all of them, all these labels, or rather integral. Okay, but as time evolves, you are not going to get a state in the far future which has only 4 particles, right? Not necessarily. In fact, in general you will not. So it's clear that the same basis is not going to be useful. Okay. So you choose another basis states, okay, which are called out states, which will be good basis states for describing well localized particles in the far future. Okay. But remember, both these bases, okay, live in the same Hilbert space. It's just different bases, but the Hilbert space is the same for the given system. It's not that you have two different Hilbert spaces, okay, but these are just two different bases which you use. One basis is good for writing down incoming states which concern incoming particles, and another basis is good for writing down states or constructing states, okay, which represent outgoing particles in the far future. Okay. But other than that, these are related by just a transformation that takes you from this set of basis states to these sets of basis states. Okay, and we had talked about all these things in detail in the beginning, and we had also defined what is the S matrix. Okay, I had written down in general with using notations alpha and beta, but now I am looking at 5-4 theory and there are no other labels other than the momentum labels. So in this case, I will just explicitly write down the S matrix to be this. So S of now I can be very specific that what the labels are exactly, meaning what alpha and beta are, okay, because there are no other labels. So as I had defined earlier, Pn, so these are the labels coming from the out states. Okay. These matrix elements are needed, right? Because if you want to express any in state in terms of out states, then you need to know these elements, these numbers, okay, or these inner products. So that is why we are trying to find out these matrix elements, okay, because then you can do a change of basis from in states to out states. Okay. So we want to know these matrix, these elements which are called as matrix elements. I am going to do something nice. The goal is that I turn these in states and out states, which are right now written using these A in daggers and A out daggers, into objects that involve the fields phi. Okay, remember we are given fields phi from our action, and if I could construct, write these S matrix elements using those fields, then it will be of course nice. And what will be very nice is that we will see that eventually this entire S matrix is going to be turned into a calculation of correlation functions or Green's functions, which we did in the previous course. Okay, so that's what we are going to show now, and this is what is called LSZ reduction. Let's see if I have some. Okay, I hope I am not making mistake with the names, but this LSZ reduction is, let's go to the next page. No, it's fine. Lehmann, Simanzik, and Zimmermann reduction formula. Okay, so this So this reduction of these matrix elements into a form which involves Green's functions or correlation functions is what is called LSZ reduction. Okay, so that's what I'm going to show you now. So let's LSZ reduction. So maybe I should write again. So this is going to be long algebra, but not difficult. This is what I write as sorry. Okay, before that I should say something. Yeah, so in this scattering which I have shown here, so let's say these are in states I'm labeling with K1, K2 and so forth, K1, K2, K3 and K4, and these are P1, P2, P3, P4, P5, P6, etc. Okay, so in general, because you have an interacting theory, it's not going to happen that these particles, when they come close together and then they give these particles in the future, it's not going to happen that that you have this guy, okay, just traveling alone without interacting with them. Okay, or more precisely, I am interested in only those contributions in which none of these momenta, okay, are left unaltered, meaning scattering really happens. It's not that some particles do not interact at all and they just keep going in their trajectories. Okay, meaning I'm not going to find any of these K1 or K2 to be equal to P1 or P2 or any of these. Okay, so I'm assuming that I'm looking at only those terms, those contributions in which interaction really happens. Okay, so this is something I'm going to utilize. Okay, good. So let's take this and I will write this as, so using our previous results, I am going to write this as P1 to Pn, that's an out state. Okay, now K1 to Km I can write as 2 omega K1, or maybe I should write it here, 2 omega K1 in the square root times A in dagger K1 acting on this. Okay, so what I'm saying is that if you take K2 to Km, these labels, this state with these labels, and you act with A in dagger K1, then that will insert the label K1 in the in state. Of course, you have this normalization and this is what you had in the previous line. Okay, so these two are equal. All I have used is this result, this one, the first line. Okay, good. Now this I will write as 2 omega K1 okay, this is something you can find at many places in Bjork and Drell and Ashok Sen's lectures and many other place it. This is standard standard thing. So now I will write this as minus A in dagger K1, K2 to Km in, okay, because I have multiplied a minus sign here, minus 1, I should multiply minus 1 here to take care of it. Okay, so this line is same as the previous line. Now I will add another operator here, A out dagger K1. Okay, but this I can do because A out dagger K1 when acts on this out state, okay, it kills it. Why? Let's go back and check. A out dagger K acting on this out state, okay, gives you this result where it removes the label Ki and gives you this delta function. But if K is not present in this list, if none of the K1, K2 and so forth up to Kn equals K, then the delta function vanishes and it gives you 0 on the right hand side, right? So you see that because I have said that none of these labels K1 to Km equals, so let's take K1. K1 is not equal to any of these labels P1 to Pn. K2 is not equal to any of these labels P1 to Pn and so forth, right? Because of what I was saying here. Because I am assuming that all the particles scatter. Okay, no one is left unscattered. Because I am assuming that, then K1 cannot be equal to any of the Pi's, any of the P1, P2, Pn. If that is so, then A dagger is going to kill this state. Okay, so effectively I have not added anything. So because this contribution is 0, so you can imagine that this is not there, and then this line equals the previous line. Okay, and that is why I am allowed to put this A dagger out with label K1. Okay, so I hope you agree that this is correct. Okay, let me write down this term. This term gives 0 contribution since K1 is not equal to any of the Pi's. Okay, and the reason being that we are assuming that all the particles scatter, none of these particles remain unscattered. Okay, none of these labels remain unchanged. Okay, good. So what? Yeah. So you have this. I will write as minus 2 omega K1, and then you have this out state here. I will just drop the labels for now, it's tiring to write. And you remember what is A dagger? Out, that involves A dagger at time t1 minus I epsilon K1, and you have to put a factor of 1 over square root of z. Let's go back and check. Yeah. Here you have, these are for out states, but for in states also. Okay, so somewhere just like these ones have 1 over root z, you had 1 over root z for A ins also. Okay, for both of these you will have 1 over root z, so I will write minus 1 over square root of z. Okay, times this minus, now what is A in dagger? A in dagger is minus t 1 minus I epsilon, and of course a dagger here, K1 and then you have K2 to Km n. Okay. Now what I'll do is I'll do a very simple thing. Okay, out. Let me just write P here. Okay. Instead of leaving it blank, I will just write P. This P stands for all these. Let me put these. Okay, let's not clutter it. So this, what I will do now is I will write this as the following: dx naught, or basically dt del naught, which is del over del t of a t, where t is small, k1. Okay. Now this is a derivative, and then you do an integral. So that integral will give you just at dagger k1. Okay, and you have to put the upper and lower limits. So if I put upper limit as this and lower limit as this, then you see that whatever I have here in curly brackets is same as what you have in the brackets in the above expression, right? Because once you have done the integral, you get at dagger, and you have to put the limits, and the upper limit is t1 minus epsilon, so that gives you this first term, minus this thing with the lower limit, which is this term. Okay, so this is identically true, and I am allowed to write it like this. Now this is useful because let's see if I can find out. Somewhere I had I don't know whether I'll find it easily. Probably not. Yeah, AP, define AT. I had given an exercise, or I had shown. Let's check. Okay, I'm not finding it, so I'll okay, so just hold on. Okay, I don't find it, so I'll just state that result. That so this del naught of at dagger was basically this box plus MP square acting on phi. Okay, this is a result you should be able to find in your notes, and I had written this earlier. So let me just use that and write it down. Okay. So you'll see that if you take this expression and use what is the time derivative of at dagger, okay, where t is small t, then it is the following. So we'll have a factor of minus I. Just a second, do I have it somewhere? Okay, anyway. So I over square root of z 2 omega k1 root 2 omega k1, and then you have this out state which I am writing in short like this, and this is integral dx naught you have anyway, and you are going to have dx cube once you put the expression for this one, del naught acting on 80 dagger. Okay, so you will have dx naught d cube x and f of k1, this is our usual f of k1, okay, which I have defined several times, times this box operator plus mp square, okay, where box is this del naught square minus gradient square, okay, this operator acting on phi of tx. Okay, this is what you will find in your notes. Okay, where these limits go from minus infinity to plus infinity, but this one goes from minus t 1 minus I epsilon to t 1 minus I epsilon. Okay, so make sure that you are able to get this expression. Okay, good. So now what I will do is two things. I will write this integral dx over dx 0 and d cube x as d4x, and I will remember that the limits for cube x is from minus infinity to plus infinity, but for the time the limits are different. They are not really from minus infinity to plus infinity, but they are along, they have some complex components, okay. But I will just drop those and write d4x, but we will remember that this is the case and we'll take care of this at the end. Okay, so with this I will get, I can write down the following. Also I will do another thing. These are just functions and simple operators, okay. So these are differential operators, but you have the operator phi, and it is sandwiched from right from this in state and from the left from this out state, okay. So I'm just going to pull out everything to the left and let phi sit between out state and in state, okay. So that's all I'm going to write now. So I over square root of z 2 omega k1, okay, that's correct, the square roots. Then you have integral d4x, and we will remember what I said about the limits, f k1, okay. Then you have this differential operator, okay, and then there's the out state. I will write it in full this time, phi tx and then k2 km in. Okay, so it's nice. I have been able to get rid of one of the labels k1 from the in state and replaced it by an operator, by the operator phi, which phi is your field operator that is present in your action, okay. And of course there are some differential operators and some simple functions which need to be integrated over, but still this is a nice result. I'm getting things which are familiar things, and now you can see almost what will happen. If I repeat the same thing which I have done just now, then I will be able to get rid of the label k2, and in doing so I will pull out another factor of phi, okay. Okay, and eventually I will be able to pull out or get rid of all these labels K2, K3, K4, Km, okay, and I will be left eventually with the vacuum omega here, and every time I get rid of one of these labels, a phi will be pulled out, okay, going by what I have done just now. That's something apparent that that's going to happen. And similarly, if I repeat similar steps for the out state with appropriate A out, okay, then I will also be able to remove these labels P1 to Pn successively, and instead of those labels, at the end I will have vacuum on the left, and I will get a bunch of phi's here, okay. So what you will have eventually is, at the end of this procedure, you will have vacuum, then a bunch of phi's coming from the out state, then a bunch of phi's coming from the in state, and then again vacuum, okay. So this is what we are expecting based on what we have seen just now. But let's see in detail what really happens, okay. What are the factors you get and what exactly is the operator content sandwiched between the vacuum. Okay, so before I proceed, I will just do one thing. I will instead of calling D4x and T and X, I will change the labels, change the names. These are dummy anyway, right? These are integrated over. So I can choose whatever name I wish to choose. Instead of T and X, I will call T1 and X1, and it will be useful to keep track of what we are doing. So I will write here 1, I will put a subscript 1, okay, so this becomes del, yeah, you understand, that's the, this is the, so this is del over del T1 square, del 2T over del T1 square minus del over del X1 square, okay, that's the operator now, and this is this, okay. So I have changed these labels because here also, because then I can remember that I have taken care of K1. So that K1, that subscript 1 on K, is now the subscript here on T and X, okay. So that way I keep track of which K I have taken care of. Okay, so good, let me write down, we have succeeded in replacing this label K1 in the in state by field phi. Now let's forget about these other factors. We will take care of these prefactors later and only concentrate on this matrix element, okay. So let us now analyze phi of T1 X1 and K2 to Km. Okay, in general M and N will be different. So, and anyway we want to get all the inner products, so we have to find for all M and all N. Okay, so now what should we do is the following. This is out state, okay. Again I will not write all these P1 to Pn, but I'll just write P. This is equal to out, then you have phi x1, okay, I will use 4 vector, So instead of writing t1 and x1, I'll just write x1. And k2, the label k2 I will again generate using a in dagger. So I will write 2 omega k2 in the square root a in dagger k2 acting on k3. Okay, I'm just repeating the steps which I have already done before. Okay, same thing. Good. So again I do what we did before. P sorry, something wrong. Yeah, this is fine. I should take out the 2 omega k2 outside. Okay, so I have phi, this is an operator, and a in dagger is an operator which are sandwiched between this in and out states. Okay, so let me write it again. Just like before, I have phi x1 from here. Then you have a in dagger k2, this one. Okay, and this is k3 km in. Okay, I want to put a minus sign, and to take care of that minus sign, I have a minus sign here. So this is right now same as the previous equation. Okay, but I will insert another term which is a dagger out k2 phi x1. And why I am allowed to insert this? Because this contributes 0. And let's see why. Because you have a out dagger with k2. Okay, and this guy acting on the out state in which none of the labels p1 to pn is equal to the label k2 is going to give you 0, right? So a2 dagger k2 acting on this gives you 0. So you have not changed the equality. And of course, if you put phi x1, that also doesn't do any damage. So I am allowed to write it this way. Okay, and I write it this way because this is useful. You can write anything else also which doesn't change this equality, but it has to be useful as well. Okay, so let's see what we gain from this. Let me write, this is allowed because k2 is not equal to any of the pi's. Okay, 32. Okay, good. Let's I think I should have given some. So this was fine. All these expressions are equal to s. Here is also s, so let me call this as a, this one as b. Okay, where b is only this part. So a is this entire equation, and this factor is what you have here, and that result is b. Now I want to take only this term in the round brackets. Okay, I should go to the next page. Okay, so now a out dagger k2 phi x1 minus phi x1 a in dagger k2. Okay, let's take this, which is exactly what you had here. Okay, and now I will substitute the expression of a out and a in terms of a's at those times, okay, at capital T. So you get 1 over square root of z, limit t going to infinity. Okay, what is a out dagger? A out dagger is a t1 minus I epsilon with a dagger here, k2. Then you have phi of x1 minus phi x1 and a dagger minus t. Remember that in states are at, they involve minus t. Okay. Okay. So this is fine, and again the trick as before. Integral dx naught del naught, and I'll put this entire thing, but this time I have to be a little more careful. Let me first write the result and then I'll tell you. Okay. Yeah. So in the previous case here, where was it? Here, I just had a time derivative and then integrated over the time, so that I would get just this and put the limits. But here I have two operators, okay, and you see the way they are ordered here in these two terms is, so x1, so you have time as t1, some time t1, okay. So the field or the operator that carries time t1 is sitting to the right, and then the operator which carries time capital T, and you remember t is going to infinity, okay. So this operator is defined at a time which is larger than the time here, right, because this t is going to infinity, so it's larger than any other time. So this operator, which is defined at a large positive time, okay, is sitting to the left. So in this term, in the first term, the operators which are defined at at smaller values of time are sitting to the right, and as you go to the left, the time increases, okay. So this one has a larger time, and let's look at this one. The same story here. This operator a dagger is defined at minus t, okay. It is a time which is smaller than the time here, phi of t1 x1, right, because this is some finite time. This operator is defined at some finite time, some t1, okay. Whatever that is larger than minus infinity, time t equal to minus infinity. So both these both the terms have operators which are defined at a lower time, okay, are sitting to the right, and the operators which are defined at a higher time or a later time are sitting to the left. So you see that these both terms are time ordered, okay. We have talked about time ordering earlier also. So both the terms are time ordered. So we have to take care of the time ordering, right. So that's what I am doing here. So I again do that same trick of taking derivative and then killing the derivative by the integral, but then I ensure that this time order is taken care of, and I put t, which is the time ordering operator, which tells you that keep the lower times, the operators at lower times to the right and operators at larger times to the left, okay. That's all it tells you, and then you take the integral and put these limits. Okay, so when this integral is done, you put the limit, it will automatically place the operators to the right and or left depending on which one is at a later time and which one is at a earlier time, okay. So this equality holds. This is a expression which is same as the above equation. Okay, so this is good, and now yeah, again you use the, let me write this down. So this is same as time order product of, if you look at the, what happens if you take a time derivative, we have seen earlier, k2 Tx and then your operator phi x1. Okay, so this is, you can write it in this form. So this del naught this is time derivative which acts on both this phi and f. Okay, so this you can verify that this result is same, the above factor is same as this one. Okay, and with this now I can write minus I integral d cube x, okay, time ordered product of f k2 tx del naught phi tx minus del naught f k2 tx. Okay, it acts on this, and then you have phi tx sorry, not here, and then you have another, here it closes here, then you have another factor of phi x1, and then this square bracket closes, this one. Okay, and this one is same as what is this? Okay, I mean it's a trivial statement, but let me write it anyway, just for ease of writing later. F k2 tx, so this factor, and of course this is time ordering, so it acts only on the operators, not on functions. Okay, so here you have two operators, del naught phi and phi x1. Okay, so time ordering operator acts on del naught phi and phi x1, so that is what I should write. Okay, I'll make sure that you verify that whatever I'm writing is correct. Tx, and then you have time ordered product of phi tx times phi x1. Okay. Let me try to times time ordered product of phi tx and phi x1. Okay, then curly brackets close here. Okay, let's call this C. Okay, now let me see what happened. Time order product of just a second, So time order to del naught phi times phi x1. This is fine. Okay. Del naught t. Okay, so there is something which I am a bit unsure, something simple actually. So maybe what I'll do is I'll continue in the next video after I have checked in my note if I'm making something wrong. So we will continue this in the next video, and you can probably already see that we are going to get not just a set of phi's. Okay, just when I pull out, when I get rid of these labels, I'm not just going to get a set of phi's, but rather time order product of a set of phi's. Okay, that is what it is going to lead to. Okay, there is something very minor which I am missing. I will check and then I will record the next one. Okay, see you in the next video.